This is an AP Chem video on assigning oxidation numbers and identifying what is reduced and what is oxidized in redox reactions. So one example of a redox reaction is what you're seeing right here, the rusting of iron. This is a reaction that causes trillions of dollars every year for the US. If we could stop oxidation of iron, that would save the US a lot of money every year. It would also reduce the number of accidents that occur due to rusting. So before we can identify whether something is oxidized or reduced, you have to be able to assign oxidation numbers. So here are the oxidation number rules. So rule number 1, all atoms in an element have an oxidation number of 0. So any element, whether it be diatomic like hydrogen, each atom in the hydrogen element is 0 for the oxidation number. If we have iron solid, the oxidation number is 0. So all elements will have an oxidation number of 0. Rule number 2, the oxidation number for a monatomic ion is its charge. So if we have an ion like Mg2+, magnesium ion, the oxidation number is +2. Cl-, the oxidation number is -1. O2- oxide is -2. Rule number 3, fluorine always has an oxidation number of -1. Rule number 4, oxygen has an oxidation number of -2 always, unless it is -1 in a peroxide. Here's the peroxide ion. So peroxides can be things like H2O2, hydrogen peroxide. Here we can see that each oxygen is -1. The peroxide ion has an overall charge of -2. And so here the hydrogen has a +1 charge for each of the hydrogens, a +1 oxidation number, since this is a monatomic ion right there. Or we could have a peroxide like sodium peroxide. Again, here each oxygen has an oxidation number of -1, and the sodium, being a monatomic ion, will have an oxidation number of +1. So again, oxygen will have an oxidation number of -2 unless it's -1 in a peroxide, or if it's bonded to fluorine, because we need to apply this rule first and then figure out what the oxygen would be if we assign fluorine -1. We'll see an example of that in the next slide. Hydrogen is always +1 when bonded to nonmetals and -1 when bonded to metals. Rule number 5, the sum of the oxidation numbers is always going to be 0 in a compound. The sum of the oxidation numbers of a compound is 0. So the total charge, the sum of the oxidation numbers in a polyatomic ion is equal to the charge of the ion. So let's look at some examples now of assigning oxidation numbers. So here we have a bunch of different ions and compounds, and we'll take a look and try to assign the oxidation number for each element in the following ions or compounds. Now, it would be a good thing for you to pause the video and try these after I've done a couple examples and see if you are getting them correct. Okay, so let's start off with A here. Here's BrO3-. This is the bromate ion. Again, here oxygen is going to be -2. So what I'm going to do is at the top above the element, I'm going to write the oxidation number. Down here, I'm going to add up my total charge, because the oxidation number is just for one of these oxygens. Okay, so the total charge here, since we got 3 oxygens, we've got -6 from the 3 oxygens. And we have to remember, rule number 5 says we need the sum of the oxidation numbers to equal the charge of the ion. So we need everything to equal -1 in the end. So far we've got -6 for the oxygen. In order to get -1, we would have to have bromine right here. We need the positive charge to be +5. That means the bromine is +5 for its oxidation number. All right, let's take a look at part B. Give it a try yourself. If you'd like, pause the video. Here, oxygen again is -2. Okay, so again here I'm going to put my oxidation number on top, okay, and I'm going to add up the total charge below. So here, if I have each oxygen as -2, -2 times 4 gives -8. The ion has a charge of -2, so the sum of the oxidation numbers have to add up to -2. So here, based on the fact that we've got something -8 equals -2, that something has to be +6. And so I look above, there are 2 carbons. So each of those carbons has an oxidation number of +3, because +3 times 2 would give us +6. All right. C, hopefully you should recognize right away, this is an element, so it must have an oxidation number of 0. Okay, letter D, we've got SF6. We can apply rule number 3. Fluorine always has an oxidation number of -1. So then -1 times 6 fluorines gives us -6. This is a neutral compound. So the sum of the oxidation numbers has to add up to 0. That means we need a positive charge of +6. And so the sulfur's oxidation state is +6. By the way, I'll use the terms oxidation number and oxidation state interchangeably. Okay, letter E. Again, here's oxygen. I'm going to apply the rule number 4 and give that a -2. I see hydrogen here. I'll apply rule number 4 and apply +1 as the oxidation number. Let me add up some charges here. We've got -2 times 4 gives us -8. We know that the ion's charge is -1, so we've got to have all these oxidation numbers add up to -1. Here, H is +1, so we have a +2 right here. Okay, so AS, in order for us to get a -1 charge, oh, I'm missing a minus sign here. Let me redraw that and put the proper charge in there. Okay, so this should be -1 because of our -1 charge. So in order to get -1, this has to be +5 because 7 minus 8 gives us -1. So the arsenic in here has an oxidation number of +5. All right, I'm going to go through the next few examples more quickly here. Hydrogen is with a metal here, so we have to apply rule number 4 where hydrogen is a -1. -2, we know this has to equal 0, so +2. This is a monatomic ion anyway, so it has its charge as its oxidation number. Letter G, oxygen is -2. That gives us -8 for this. It is a compound. There must be an overall charge of 0. Here, hydrogen is +1. That's +4. So we need another +4 for the silicon. SO42 minus, oxygen is -2 again. That gives us -8. The charge of the ion is -2. So we need +6 for the sulfur in order to get a -2 overall charge for the ion. N2O4, again, this is -2 for the oxygen. Okay, -2 times 4 gives us -8. The overall compound's charge is 0. We need a +8 here. So each of these nitrogens has a +4 oxidation number. Finally, J, our overall, this is an ion. Our charge needs to add up to +1. Okay, Cl is a monatomic ion here. We're going to give it a -1 charge. -1 times 4 is -4. And then in order to get a +1, we need a +5 for the phosphorus. And there we go. We've assigned our oxidation numbers. Just keep in mind here, these things on the top, these are the oxidation numbers. And they are for each atom in the compound. And down here, we're adding up the charge. Okay, so that we make sure that we end up with the charge of the compound, which is 0, or the charge of the ion, which is given to us. All right, so now that we know how to assign oxidation numbers, let's see if we can identify in reactions, okay, whether reduction, and oxidation is happening. So in order to classify these reactions right here, to identify, it says here, which of the following reactions are oxidation reduction reactions, we're going to have to assign oxidation numbers. And if we see oxidation numbers changing, okay, this is kind of the crux of redox, right? Oxidation numbers must change in order to have a redox reaction. And I'm just going to abbreviate oxidation reduction as redox. So we need to have changes in oxidation number in order for us to have a redox reaction. If we see no changes, it's not redox. And in order to see the changes, we have to correctly identify the oxidation numbers. So going along here, I'm going to look at A. I assigned 0 for zinc. Okay, here's -2 for oxygen here. So -2 times 3 gives us -6. The overall ion is -1. This has to be a +5. So our nitrogen is +5 here. Oh, hydrogen's already given to us. It's +1, same as its charge. Here again, +2, same as the charge. Here, oxygen is -2, -4, +4, because we need an overall charge of 0, +4 here. H2O -2 for the oxygen, +1 for hydrogen. And if we look across here, do we see any changes in the oxidation number? Pause the video and see whether you see changes. So I see some changes. Let me highlight these changes in blue here. I see zinc changing to +2. Now, it's not enough to see one change. Okay, we need to have an oxidation and a reduction. So we need an oxidation. This is an oxidation. Okay, because the oxidation number increases. We are losing electrons. Let's see if we can find something that is getting reduced. Here we go. Nitrogen is going from +5 to +4. This is the reduction. The oxidation number is going down. Therefore, electrons have been gained. So this is a redox. Yes, redox. This is a redox reaction because we have an oxidation and a reduction. Remember, in a redox reaction, oxidation numbers must change, and we must have oxidation and reduction. Both have to be occurring. Okay? Otherwise, we do not have a redox reaction. It can't happen unless you have an oxidation and a reduction. All right, look at letter B. Well, I'm going to show you a quick and dirty way to figure out whether something is a redox or not. Well, if I look at this, this is a double replacement. How do I know this? because I see that this is a base and an acid. Let me put that in parentheses, acid base. Not redox. Okay, so all double replacements are not redox reactions. Okay, never. Double replacements are never redox reactions. So if you can recognize that a reaction is a double replacement, then you can immediately say, oh, it's not redox. All right, let's look at C. Now, if you look at C, maybe you recognize what type of reaction this is. Here, the calcium is kicking out the hydrogen. This is a single replacement. Single replacement. And guess what? We're in luck today because single replacement is always a redox reaction. Always redox. Okay, so here's a single replacement. Just to check here, our calcium solid is 0. Our hydrogen is 0. Now, if we look in our water, we know hydrogen is +1, the oxygen is -2. Here in calcium hydroxide, we've got the monatomic ion, that's +2, and then oxygen is -2, and hydrogen is +1. So we can see here, I switched colors, I see, but that's okay. Calcium is going to +2. What's that? Is that oxidation or reduction? That's oxidation. And here we see hydrogen going from +1 to 0. So is that oxidation or reduction? Well, we already said this top one is oxidation, so this must be reduction. And this is oxidation. Again, here the numbers are going down here. Oxidation numbers are going down, so that's reduction, reducing, going down. Oxidation numbers go up. That's oxidation, okay? That means electrons are being lost. So in number 3, we're going to decide which reactant is oxidized and which is reduced. So let's see, how do we do this? How can we decide whether something is oxidized or reduced? We must assign oxidation numbers first. Okay, in order to see whether something is oxidized or reduced, we need to see whether the oxidation numbers change. So let's look at A. Let's assign our oxidation numbers, then figure out what's oxidized and what's reduced. So I look over here. Oh, I see oxygen, the element. So I like to do elements first just because they're quick and easy. Hydrogen, rule number 4, +1 when with a nonmetal. So that means we got a total of +4 here for hydrogen. It's a compound. The overall charge has to be 0. So this has to be -4 for 2 carbons here. So that means each carbon is -2. Okay, we've assigned that. Let's go over to CO2. -2 for oxygen. That's a total charge of -4. Our overall compound is 0. This must be a +4, so our carbon here is +4. Here's water, oxygen -2, hydrogen +1. All right, so let's take a look. Let's figure out what is changing in oxidation number. So when I go here and look, my carbon is going from -2 to +4. -2 to +4, the oxidation number is going up. It is losing electrons. That's my oxidation. Where's my reduction? Okay, my reduction is here. My oxygen is going from 0 to -2. There's my reduction. Okay, so what am I going to say is oxidized? C2H4. Okay. Sometimes people just say the carbon is oxidized, or we can just say the whole compound is oxidized. It's hard to separate out the carbon in there. It's bonded in. What's reduced? That would be the O2, okay, or the oxygen. All right, I would pause the video at this point, assign all these oxidation numbers, figure out what's oxidized and what's reduced, and then play the video and see if you are correct. Okay, the way to make sure that you're learning this material, that you're absorbing it, is to test yourself and to practice. Okay, without having the answer first. I used to deceive myself that if I, sometimes understood something, if I could understand the answer, but that really doesn't help you. It helps if you practice it and then check and figure out where your understanding is weak or where your understanding is just not present. So got to try it first. All right, so pause the video and give B and C a try, and then play the video and check your answers. Okay, B here. The dichromate ion. So our ion has an overall charge of -2. So our oxidation numbers, our charge down here needs to add up to -2. Our oxygen has an oxidation number of -2. That's a total of -14. Okay, that means in order to get -2, this has to be +12. And there are 2 chromiums, so each chromium is +6. All right, we assigned that. Okay, this one's easy. It's just +2. This one's easy. It's just +1. Here we got +3, +4. And here's our water again, always +1 for hydrogen, -2 for oxygen and water. So we've got to find what's changing. Okay, so let's look at the elements here. I see that chromium here is going from +6 down to +3. Okay, so that's going down. What other changes do I see here? Well, I see that tin is going from +2 to +4. All right, so let's see. +6 to +3, that is going down. That's the reduction. +2 to +4, that's going up. That's the oxidation. So what's oxidized? That would be the SN2+. What's reduced? That would be the Cr2O7, 2-, okay, or the Cr. Okay, we could just say Cr is getting reduced. Okay, our final one, letter C. Let's assign the oxidation numbers. So here we have a ionic compound, monatomic ions. We can just use their charge as the oxidation numbers. Okay, here oxygen -2 as always. So that would be -6. The overall ion charge is -1, so this has to be +5 for the nitrogen. Here we have the oxidation number. Again, here oxygen -2, so nitrogen is +2. Here sulfate has an overall charge of -2. Our oxygen has a -2 oxidation number, that's -8. So we need +6 here for the sulfur. Here's our oxidation number for Fe, and water is +1, -2 as always. All right, so let's look for the changes. So we can see here that Fe changes to Fe3+, goes from 2+ to 3+. And this is unusual in that sulfur here is also changing oxidation number. It's going from -2 to +6. Is there another change that we can see? Yeah, here's nitrogen going from +5 to +2. Okay, so here for the iron, we're going from +2 to +3. The number is going up. We're losing electrons. That must be an oxidation. The sulfur goes from -2 to +6. Again, the number is going up. This, again, is an oxidation. The nitrogen is going from +5 to +2. The number is going down. It's gaining electrons. That is a reduction. So what can we say is oxidized here? FeS, the substance FeS, is getting oxidized. Both elements in FeS are getting oxidized by NO3, which is getting reduced, NO3 minus, okay, or the nitrogen in NO3 minus. Okay, so I hope this video was helpful, and after watching this, hopefully you know how to assign oxidation numbers and determine what is oxidized and what is reduced in a redox reaction.